In today's tutorial, I will be talking about interpolation. First, I'd like to bring your attention to this paper, uh, and it has a lot of interesting stuff, uh, especially with membrane simulations. They have like stuff on like cloth and ropes, but today the main purpose for looking at this will be for this little section at the end in the appendix where they talk about interpolation functions. And here is this is a really nice resource for you to help you figure out how to implement this kind of stuff. They have the formulas for the weights for each node, and also the formulas for each gradient. So like I think like the gradients especially trip people up when they try to implement it, because finding the gradient might need like some experience in calculus. I actually when I did this, I didn't know this paper, so I just found derivatives and stuff, and it's not that difficult, but I can see why like it might be difficult if you haven't had any calculus stuff. Anyway, so this is basically it. Now I'm going to show you a little bit of code for this that I wrote, and it's not the best code. I kind of did it in a hurry. I didn't even make it very object-oriented, so you can see I'm using like a three-dimensional array for this little grid over here. Anyway, my variables are slightly different from the paper's variables, but it's basically the same idea. You can see this section is it's the weights for each of the cell corners, and over here I just add the particle mass to the grid. This is the mass variable. It's just something really simple. Every particle has the same mass and stuff. It's just to illustrate this concept. Anyway, this is what linear interpolation looks like. I'm going to run this applet, and it's just going to draw all the particles. And basically, you can see I interpolated all the particles to the grid, and then I I scaled up the image a lot, where each pixel became like 20 pixels wide. So this is like linearly interpolated, and everything is like really huge. And once you scale it up this much, you begin to see that there are actually quite a few artifacts. And in my algorithm, I use this interpolation thing to sum up the density of the particles. So you can see that with the kinds of like little folds and stuff that this creates, that would mean quite a bit of grid artifacts. Like there would be like a bit of really nasty clustering and stuff, and also there'd be like some popping because of some of the instabilities that this causes. Anyway, in this paper, they suggest using the quadratic interpolation function to sum up the density around the particle. The quadratic interpolation is slightly smoother and it gives better results, but the bad thing is it more than doubles the number of cells that you have to interpolate to. while also making the equations more complex with squares and stuff. And there are a bunch of gradients you have to take care of also. And in 3 dimensions, this 9 neighbors would become 27. So you can see why quadratic interpolation might not be the best choice. So in my simulator, I did a little bit of a compromise. I stayed with the 4 neighbors around the particle, but I added some extra data to the grid. And basically I have on the grid, I also store the gradients of the mass. So for each particle, I'm also adding the gradients to the grid. And then when I interpolate again, I'm going to switch the gradient correction on. First I take the mass that's stored with each grid node, and then I add the dot product of the vector from the cell corner to the particle. So the dot product between that vector and the gradient, the mass gradient that's associated with that node. So this is just a simple dot product over here. And basically what this looks like is this. Now it's not perfect. There's still some grid artifacts, basically in areas like this, or this, or here. But it is slightly better. The boundaries are slightly more rounded, and everything is slightly smoother. And actually where the artifacts are, most of the time they don't really affect the particles. They're not really at places where particles are at. Now, I must give you a word of warning that sometimes the gradients might make your data slightly worse. But in my simulator, I'm still working on I actually do a little bit of like half and half. I have like this little threshold thing where I switch between simple bilinear interpolation and gradient corrected interpolation. But I haven't really perfected it yet. It's just some kind of like magic number kind of thing. Anyway, if you have any ideas on this, you could comment on my video or something. Anyway, I think that's all for today's little tutorial on interpolation.